quantum adjustment arises when when a payoff is defined in one currency, but is paid out in a different currency. Now, for example, if there's a contract that pays you in Canadian dollar, the S&P value or the S&P index value, that you would require quantum adjustment, because S&P is a index that's defined in the US dollar. But in this case, the contract pays you the value in Canadian dollar. So in a case like that, you will need to have a quantum adjustment. Now, another requirement for quantum adjustment is the conversion rate between the two countries is stochastic over time. Basically, it means that exchange rate is stochastic. So you will see that this quantum adjustment is really another application of change of numeraire when we're trying to take expectations. So first of all, let's take a look at some of the terms we defined to help our analysis. So this PX here is the zero coupon bond for denominated in currency X between time little t to the big T. Likewise, PY is the price of zero coupon bond denominated in currency Y between time little t to time big T here. V is some sort of a variable or some levels, right? So in the example we had will be the S&P 500 index, okay? And so the payoff may be at T, and so you need to observe this value, the S&P 500 index at time T. Here, we define the expected value of this variable V at T. X means that we were using this zero coupon bond PX as a numeraire, whereas EY means that we're taking expectation using the zero coupon bond PY as a numeraire. And S is the spot exchange rate at time T, expressed as units of Y per unit of X. So the spot exchange rate that expressed as unit of X per unit of Y will be 1 over ST. Okay, now let's define our usual variable W here. W is this ratio PX divided by PY. You can sort of see that we're changing from one numeraire PY to numeraire PX here. So we then, for notation purpose, we have a sigma W for volatility of this variable here. And we have a volatility of V, whatever the index level that we're looking at. So maybe S&P 500. It doesn't have to be an index, it's just some reference asset there, which value is denominated in one currency, but you want to pay that particular number in a different currency. Now you have an instantaneous correlation between V and W that you defined here, and that correlation coefficient is this rho here. Now, if you define the W this way, so what is W, right? Well, W is actually the forward exchange rate at time T. Now for the forward exchange rate at T, you can see that with this expression, you can write it as W divided by this PX is equal to ST divided by PY. So why they're equal? Well, let's say you have $1 Canadian and you convert it with ST to X number of dollars in US, and you divide it by PY means that you invest under a rate, say this PY is a 1-year rate discount factor. So 1 divided by this PY allows you to invest that at the US interest rate for 1 year. Now this is same as $1 invest at PX, so which is the Canadian interest rate there. And then once you got the $1 Canadian invested under the Canadian interest rate, and then you convert it to US dollar, and you'll get the same amount. So that's why this is the forward interest rate. Or if you look at it differently, you can see that this px times st is really, you have a currency y here at time t per unit of x at time big T, because this is the discounting factor. And then you divide this thing here by this py, then converts it to 1 unit of x at time big T into a unit of y at time big T. So if you have $1 Canadian, you can take this discount factor. So basically $1 Canadian at time big T, you'll through this get the present value at little t of the present value of that $1 Canadian. And you can use this exchange rate to convert to US dollar at the little t. And then, which is the same as, it should be the same if you then invest that Canadian dollar, US dollar, you get at this point for that $1 worth of Canadian dollar at big T in this, because you divide it by this, so you're investing with this factor here to convert it to how many US dollar you have at the big T. Okay. Now let's look at an example here. So you have a 6-month forward price of Dow at 22,000. The forward price has volatility of 25%, and the 6 months US interest rate is 3% per annum. The 6 months Canadian interest rate is 2.5% per annum, and the current US dollar per Canadian dollar exchange rate is 0.7352, and the volatility of that exchange rate is 10% per year. The correlation of Dow 30 index with the forward exchange rate is 30%. Now, in this example, we have a contract that traded at TSX. So it provides the payoff in 6 months in Canadian dollar, equivalent to this Dow index at that time. So here, this 22,000 is the forward price, is the price, the forward price that we observe right now at T0. And whatever the realized value of that Dow 30, this contract will pay you that in Canadian dollar. So the question is, how are we going to price this contract, VCAD? So what is VCAD? Well, you look at it, you get a payoff in Canadian dollar at time T, big T. So this VCAD, if we express in that equivalent martingale approach, should be the zero coupon bond. You can do that in terms of zero coupon bond PCAD, the Canadian dollar zero coupon bond, from little t to big T, use that as numeraire, then the initial value here is equal to the discount factor times the expectation of this index value at time t, but the expectation is taken consistent with this being the zero coupon bond, this zero coupon bond as a numeraire. Okay, so this is what we need. Basically, this expectation is what we need. So what is this expectation? Well, if you look at it, we see that this expectation value is not given directly in the question, because in the question, we're given this value. This value is actually the expected value of VT, but it's using the PUSD bracket little t, big T, using that zero coupon bond as a numeraire. So it's an expectation, but it's expectation under two different measures because we have used different numeraire asset. So we need to convert this expectation into this expectation. And then once we have done that, we can just multiply by the Canadian discount rate, and we'll get the value here in Canadian dollar. So we have to do the adjustment here. Well, we know that to adjust from this expectation to that expectation, we need to go through an adjustment factor, which is equal to this. This is basically a change of the drift. The drift change is alpha, and because we're doing log normal, that's e to the power of this drift change. So now, all the information is not given by the question. So correlation coefficient is 0.3. Sigma W is really this 0.1 times square root of 2. Sorry, 0.1 times the square root of 0.5. And this sigma V is 0.25 times square root of 0.5. The annualized volatility is 10%, but we're looking at the contract 6 months. So we have to multiply this by square root of 0.5. And same by the same token that volatility, annualized volatility of the Dow 30 is 25%. And again, because it's contract 6 months, so we have to multiply by square root of 0.5 here. So if you just plug in the formula here, you will get an adjustment factor alpha, which is equal to 0.00375. So your expectation of this VT under Canadian zero coupon bond as the numeraire is this US one times this adjustment factor 1.003757 e to the power of this, till you get this being $22,082.65. Now then just discount it by the Canadian zero coupon bond, the Canadian discount factor, you will get this value in Canadian dollar.